Hello, everyone. Good morning, good evening, good afternoon, depending on from where you are joining from. So today we are going to talk about distributed training at scale. So before we get started, let me share my screen and the presentation. Okay, so first of all, before we get started, I just want to make sure that you are aware of what we are going to do in next 1 hour or 1.5 hours. So we are going to get started with distributed training. So if you have never worked in distributed training or you have just heard about it or want to explore or you just got started, this might be a good informative session. And my whole intent would be to make sure that you make the best use of this 1 hour or so, right? So all the materials that we are going to cover, we are going to share it with you. I'm going to put that in the chat after some time. But whatever we are going to present, you will have that, right? Be it presentations, source code, and how to get started in the lab environment after this session. We will share this. Okay. If you have any questions, feel free to put that in chat. I'll try to answer it as we go along. Otherwise, I'll be more than happy to discuss offline after this session, right? Considering the time that we have. Okay. So before we get started, I would like to thank a couple of my team members, like Bill, who is from our marketing team. So you might have received the email for this webinar. So he has done a lot of work in the backend. So I would like to thank him for all his hard work. Marwan is also from one of my colleagues. He's from our training and professional services team. So a lot of content that you see is motivated and developed by him and his team. So if you have ever taken or if you take any Anyscale training, corporate training, there is a high likelihood that you would meet Marwan. Okay. All right. So let's get started. So first, why we need distributed training or why we are even thinking of distributed training in the first place, right? So let's think about it. Like when we think about training, what are the components that we have? We have the model and we have the data. So this model could be any model, right? A GPT, a Llama, XYZ. And why we need to think about distributed training is because of this fact that GPU memory is constrained, right? We have a certain amount of GPU memory. Now, for the sake of the discussion, let's assume that we have enough memory in the GPU that we have here to accommodate the data and the model, right? So let's assume that. And let's say this amount of data can be trained in, let's say, 1 hour. Now we cannot do anything more. The memory is full. So how can we get started with the training? Let's say we increase the data. Now we have 4 times of the data. So in this case, now it would take 4 hours. If previously it was taking 1 hour, now it would take 4 hours. Now, how we can make it more efficient, how we can make this fast? One way to do that is we will have multiple GPUs or multiple machines, and we will distribute the data. Now, in this case, every machine or every GPU can do the training at the same time. So now, effectively, we are able to train at 4 times of the speed that we could train before, right? But when we are training like this, there must be something that we have to be careful about, right? Because all this training is happening at the same time. So at the end, all these 4 models are basically one single model. So there must be something that we need to do, right? When we scale out. So let's see what we need to do extra when we perform a training like this, where we use the same model. The same model is copied in all the GPUs, but different set of data is passed. So before we understand that, let's see what goes inside the model. So inside the model, we have parameters, gradients, and optimizer state, right? So this is typically what a model comprises of. And since the model is same, in all the GPUs, we will have the same thing in all the GPUs. Now, if you see here, the optimizer state, the blue box is a little thicker. It's exactly the double of the parameters. Is because we assume that the optimizer is, let's say, Adam. So for Adam, if you have 100 parameters, in Adam, if you use, there will be 200 parameters because of first moment and second moment. So basically, this is what the model comprises of. And we have the same model in all the 4 GPU. So let's see what happens in the forward pass. So in the forward pass, the whole data set goes in and it performs the forward pass. Very simple. There is no need to communicate across multiple machines. Now, once that forward pass is done, we will start the backward pass. Now, when this happens, after the backward pass, we will have gradients in all these machines. Now, since there are 4 different batch of data went through, the gradients will be all different. Now, at this point, if we just update the parameters, what will happen is we will end up getting 4 different models. So we don't want that, right? We want a single model because this is what it is, right? We have a single model. We are using 4 GPUs because we wanted to make the training faster. So this is the point when all these GPUs need to talk to each other and make sure that they have the cohesive gradient or the gradient accommodating all of the changes, right, in that distributed fashion. And this is what is taken care by the NVIDIA. Let's say if I consider NVIDIA GPU, this is taken care by the native NVIDIA primitive called all reduce. So what it would do is it will just accommodate or add all the gradients. And after this point, all the GPUs will have the same gradient. Now, while this is happening, the GPU is completely idle because they are now communicating across each other. And when we say idle, that means there is no computation happening. Okay? Of course, the GPU is waiting for the other GPU to send the gradients. But when we say it is idle, we are thinking from a standpoint of computation. Okay, so this is not good, and we will come back to that. How we can optimize this, but this is needed. So once this is done, once all the GPUs get their gradient, they can update the parameters based on the optimizer state, right? And once that is done, we can start with the new batch of data. Okay, so that's what we call as distributed data parallel, where the model remains the same in all the GPUs. It's just that data is different, and we train the model at the same time across all the GPUs. But it's just that before making those changes in the parameters after every after every backward pass, we have to communicate with each other, right? Now, the assumption that we made here is the model can be accommodated within one GPU. If you see here, the whole model is inside one GPU, right? There is no sharding here. So we assume that we have enough GPU to accommodate that. But what if the model doesn't fit? In that case, what we can do? So that means the model is so big that we cannot have it in one GPU. So in that case, there are different techniques that we can think of. One of the most common technique is, if you look at this, if you just look at these 3 components, if I know that I don't have enough memory, what I would do is I would try to shard, or I will try to distribute the component which consumes the maximum amount of memory. And that is the optimizer state, right? Because this takes the maximum amount of GPU memory. So in that case, what we can do is we can now keep the parameter and gradient same in all the GPUs. That means we will have the copy of parameters and gradients, but optimizer state we will shard. So the first GPU might have the optimizer state of first 25% of the parameters, and next 25% would be here, next 25% would be here, and next 25% would be here, right? So if you have 100 parameters, the first 25 optimizer states for the parameters would be in GPU 1, and the last 25 would be in the last GPU. Okay, so if we do that, what we get is 0, 1, also called zero redundancy optimizer, and this is where we shard the optimizer state. But let's say this is also not good enough. Our model is so big that we cannot accommodate this. So what can we do? We can next optimize the gradient as well. So we will shard the gradient along the way. And we have not discussed about forward pass and backward pass for 0, 1, but you can guess that now that we are sharding, we need to communicate even more, right? Because previously for distributed data parallel, everything was a copy. But now we are sharding. That means in our forward pass or the backward pass, we need to do more communication, right? We are not getting into the details of that, but just wanted to give you an intuition of how distributed training works, right? And when we do this, when we shard the optimizer state and the gradient, what we get is 0, 2. And by now, you might have got the intuition, if we still need to optimize, let's say the memory is not enough to even accommodate this, the model is so big that we cannot even live with this, the last thing that we can do is shard the parameters as well. Right? And this is what we called 0, 3, which is typically mostly used in real world production. This is also called as FSDP. It's just a different implementation. So 0, 3, I guess it's from Microsoft or DeepSpeed, and FSDP is the Meta or the PyTorch implementation. But underlying, it's the concept is exactly the same. It's just the implementation difference. Now, we are going to cover FSDP in our next webinar. I will share the details towards the end, which is, I guess, 2-3 weeks from now on 19th of February, where we will go into the details of FSDP and how this forward pass, backward pass works, right? But from the implementation standpoint, when we go to the code, you will see that it's just few lines of code change. That's very trivial, right? So this is what distributed data parallel is. And if you think about it, although we have 0, 1, 0, 2, 0, 3, collectively, all of these techniques are called data parallel. And the reason that it's called data parallel is each GPU still compute the full model forward pass and backward pass for each batch of data. That means it is not like you pass some data, and while that forward pass is happening, it goes from here and then come to the second GPU, and then output of this goes to the third GPU, and like this. This is not what is happening, right? This is there are different techniques for this when the model is so big that you have to do that. So here, this data is going through the same GPU and coming back from the same GPU. The forward pass and backward pass is happening at the same, in the same GPU. It is just that, what is the difference? It is just that we are changing how the model parameters are stored in the memory. In distributed data parallel, we stored everything in the memory. But in 0, 1, 0, 2, and 0, 3, we are not storing all of the parameters at the same time. But when we need, we have to communicate. For example, if you see this 0, 3, we are sharding everything. So now, if we have to do the forward pass, I cannot do the forward pass here because I just have 25% of the parameter here. Similarly, this has 25% of the parameter. So in 0, 3, and this is something that we will go deep into in the next webinar, but in 0, 3, when we do a forward pass, before even you do the forward pass, you have to do a communication where you take all the parameters that are needed to make the forward pass. Similarly, in this GPU also, it need to talk with all the GPUs and make sure that it can take the forward pass. And once that forward pass is done, it will just drop everything and it will continue with the next step. So at any point in time, in 0, 1, 0, 2, or 0, 3, it has to have the memory to accommodate a single layer or the single component that it is performing. So one way to think about this is, let's say, I live in a small 2-bedroom apartment, and I have invited 20 people for a day outing. I mean, not outing, for a day hangout, where we decided that we will have breakfast, lunch, and dinner together. Now, those 20 people cannot stay, in our small apartment, but we decided that we have to eat lunch, breakfast, dinner together. So what we can do is we can inform our friends that you go and stay wherever you want nearby, but during lunchtime, just come. So that means if you now think of this dinner, lunch, breakfast as forward pass or backward pass, that is what it is. But once that is done, they are distributed, right? So I'm not accommodating them, throughout 24 hours in the day in our home because there is no space, which was possible if I just have 4 or 5 friends and they can all stay throughout, right? So at the end of the day, in 0, 1, 0, 2, 0, 3, the forward pass and backward pass is still happening in the same GPU. So that means the data is not moving from here to here, right? So that's the only point. But let's say, we don't have enough memory to temporarily to even perform the forward pass or backward pass. Can we even scale further? And the answer is yes. There are different techniques like tensor parallel, pipeline parallel, and so on. Okay. So that's about distributed training, right? Now, before we jump into the code, let's see how you can do this with Ray, right? And before we jump into Ray, let me give you a brief about Ray. So Ray is a distributed compute engine for scaling your application, which is predominantly used for different AI workloads. And to get started, you can just simply pip install Ray in your laptop. And after you install, what you get is Ray core. And now with this, you can imagine that your laptop has become a cluster where you have all the workers, which are your GPUs and CPUs, whatever you have in your laptop. So you can think of it as a single node cluster where all the resources in the form of GPU and CPU, Ray can utilize. And what it can do is it can parallelize your Python application across multiple CPUs and GPUs. And you can start with your laptop, but you can very well run it in any cloud platform, be it AWS, Google, Azure, etc., right? And the same code, same semantics. It's just that you have to make some changes in the config, and the code semantics or API will remain the same. Now, this is about Ray core, and just to give you an intuition of how that works, when we say scale the application, let's say you have this simple Python function. There are 2 Python functions, and I'm just calling the embedding function and then passing it to the similarity function, right? Very standard flow of execution. Now, if you run this in your laptop, it will be in a single thread. One CPU would be used, and it will be in sequence, right? Sequentially, it will execute. Now, let's say you have multiple CPUs and multiple GPUs in your machine. How you can make it distributed? You can simply decorate this function with ray.remote. And the moment you do that, this is just the definition. Just pay close attention here. Previously, we were just calling the function like this, but now we will call the function like this, right? Because it is no longer a function. It has now become something called Ray task. And what does that mean? It means that, let's say you have 2 CPU, and what this can do is the first one get executed in CPU1, and the second one can get executed in CPU2, and both are running at the same time. And they will not return the output of that function. What it would return is a reference, right, which is an object reference, or you can think of it as a pointer. So that's why it's very instantaneous, right? And in the back end, the execution starts. So your flow continues, and everything is just it returns you a pointer. Right? And when you do ray.get, you actually get the response. This is a blocking call. So unless and until these two operands, these three operations are over, this will just wait, right? But this is how you can make your application, parallel. This is just a simple example, but this is how you can do it using Ray core. So imagine like this is a simple example, like you have 8 images and you want to perform some data processing across 8 images. How will you do that? Using regular Python, you will just sequentially go over each machine, each image, and perform that. But now with Ray, with just decorating that function with ray.remote and calling this using remote function name .remote, it can make use of all the CPUs in your machine without you knowing it, right? So you don't need to be a distributed system experts and all that, but you can very well continue with this, right? So that's about Ray or Ray core. Okay, so now what I will do is, let me just skip through a few of these slides because I just want to give you an intuition of how this Ray works under the hood. And now, if you think about it, what we just saw is Ray core, but in real world, there are a lot of AI workloads which has a standard API. So be it data processing, reinforcement learning, training, tuning, etc. So what the team at Ray thought was, okay, the user or the developer can always use this decorator and make their application scalable. But why don't we make their life even easier by adding few AI workload specific libraries which can make their life easy? And that is what we are going to see today. And to do this, all you have to do is previously you installed Ray like this, pip install Ray. Now you just have to install pip install Ray and then data for data processing, train for training, tune for hyperparameter tuning, and so on and so forth, right? So I just want to give you an intuition of how things are stacked, right? So in today's webinar, we are going to talk about Ray Train, but it also have a support for other engines in this ecosystem like VLLM, PyTorch, Hugging Face, etc. But today we are going to talk about Ray Train with PyTorch. Okay, so that's the premise of distributed training and where Ray stands. We are not covering, how the Ray cluster is created and what are the components in that. If time permits, I can take that later. But now let's go to the code and see this. But before that, I just want to give you a visual intuition of how distributed training is done, let's say without Ray. So now let's talk about how we can do a distributed training only using PyTorch. Okay, so the way that you will typically do using PyTorch, and the way that you should think about it now is you have one machine with, let's say, 4 GPUs, right? And you are writing a code to perform a training across those 4 machines. 4 GPUs. Okay, the concept will remain the same even if you have multiple GPU across multiple machines. But just to give you an intuition, let's think through that you have a machine with multiple GPUs and you are performing the training. So the first thing that you need to do when you use a vanilla PyTorch is you have to tell PyTorch that, hey, look at this code and make sure that this code should run on a distributed fashion or in a cluster of GPUs. And that's what you need to do by setting up the distributed environment. Right? And we will see that in the code as well later on when we go to the notebook. But this is where you are instantiating the distributed training setup. You are initializing the group, and you are giving that backend as NACL, because this is what NVIDIA GPU holds, and this is the entity which will take care of that all reduce, like the GPU to GPU communication whenever there is a need. We talked about all reduce, but there are different other APIs that exist for GPU to GPU communication, right? So this is the setup which enables GPU to talk to each other. Okay. Once this is done, we have to make our model to select what type of distribution technique that we will use. In this case, we are wrapping it with FSDP, but it could be DDP, FSDP, whatever. Whatever you import from here using torch.distributed, you just have to wrap your model with that so that PyTorch understand what distributed technique or parallelizing technique that you want to use for this training. So in this case, it is FSDP, but for DDP also, it's just the same. Once that is done, the next thing that we need to do is we have to do the data set preparation or data loader in a different way, because now we want this 4 GPUs to have 4 different micro batches. We cannot send the same batch to all these 4 GPUs. In that case, there will be just 4 same training happening at the same time. We don't want that. So that's why we cannot just simply use the standard data loader. We have to use distributed sampler. So that is something that you need to define here. So now there are 3 things we have done. We have set up the distributed training environment. We have prepared the model, and we have prepared the data set. Once these 3 things are done, we can go ahead and run the training loop. And the way that you will execute this code is using torch run, not like a regular Python. You can always do that, but torch run has a lot of benefit in running the training code in parallel because it sets a lot of environmental variables like the GPU, naming and system configurations and all that, right? Rank and everything. So now, if you see how we can do this with Ray, you have 2 things to do with Ray. One, you just have to import raytrain.torch because this is a PyTorch code, that's why. And you just have to import prepared model and prepared data loader. That's all, right? And then you will take the same model, whatever model that you have before, you just have to pass it through prepare model. And you can take the same PyTorch data loader and send it through prepare data loader. That's all. So you don't have to do this distributed sampler, and you don't have to do all these setting up the environmental variable, distributed environment and all of this. Everything will be taken care by Ray Train Torch under the covers with prepare model and prepare data loader. Okay, under the hood, it uses this, but you don't have to worry about that. And once this is done, then you can start the training. And how you can start the training? You will use something called torch trainer, which is kind of the driver, and you will pass the training function, which is the same training function that we have. And then we have to provide the scaling configuration. That means how many GPUs you want to run and how many, whether you want a GPU or not. So in this case, we want this training to happen in 16 workers, and we are saying that use GPU. That means 16 workers means 16 GPUs, right? So you have the full control of where you want this training, and it will just start. So just to give you an intuition of how it works under the hood, let's say this is your training code, and we have some configurations, right? Scaling config, running config, and all that. And now, when we think about Ray Train, this is the combination, right? So the training function and all the configuration together, we call it as Ray Train. And we import Torch Trainer, we import all the configurations. And then the moment we have this Torch Trainer with all this config, what happens under the hood is you run trainer.fit, and your training function get distributed across multiple workers defined in your scaling configurations. Define whatever you have defined in the scaling configuration. So here we have defined that use 4 workers. So that's why it got it has been 4 workers. If you give 100, it will be, let's say, 100 workers, provided that you have that many number of GPUs in the machine, and it can perform the training. Okay, so that's about the distributed training part. So now let's go to the code, and let me show you that in action. Okay, so if you have any questions, maybe you can put that in the chat. I cannot see any questions so far, so give me 1 second. Okay, yeah. So now what we are going to do is we are going to share this GitHub repository. So if you see here, this is the GitHub repository that we will be sharing with you, and I can put that in the chat as well. And there is a blog post which I will discuss a little later. But now let me show you the code. But before I jump into the code, let me tell you where I am now. Right? So this is in my local desktop, and I've opened a cursor, but it is connected to a Anyscale workspace. So if you log into Anyscale, so let me just show you this. So if you come to console.anyscale.com, if you just log in with your GitHub or Google, or if you have an account, you can just log in. Once you log in, what you will get is something like this. You will have a dashboard like this, and there is something called workspace, and here you can just create a workspace. And what it will do is you give any name, like let's say demo, and you can have some configuration, like what kind of machine that you need. You can just mention that, and you can add some worker nodes. And this is the machine where the actual training will happen. And the head node is kind of the driver from where you will start the training. Right? And then you can just click on create. And once that is done, what you will get is something like this. You will get some workspace like this, and this will provision and configure your cluster under the hood without you worrying about that Ray install, what you would typically do in your laptop. You don't have to worry about all this. And then if you come to this Visual Studio Code and click here, and you can very well do this here on the browser, or you can open it in cursor in your desktop or in Visual Studio Code, whatever you feel like. So I just clicked here, and that's how I end up coming to this page. Right? And I can see all the folders that I have in this present working directory. Okay, so I've just cloned this GitHub repo. You may like to do that as well after this webinar to run through this code. Okay, so so let's see, how we can do this with PyTorch, right? So this is a very simple PyTorch implementation, and in this case, we are not doing any distributed training is a simple, straightforward one GPU training where we pass the model, do the forward pass, then do the backward pass, update the weights, and save the checkpoints, right? This is something that you would typically do even if you run the training in your laptop, right? So first, what we do is we create the data loader, and this is where we are creating the test data set, the training data set, and then we are using the data loader to create the test and training data loader. It's simple PyTorch. There is nothing here about distributed training yet. Okay. And then we have the training function where we get this data loader, from the function that we have just seen. We define the model. In this case, it's a vision transformer model because we are doing a image classification task on Cipher 10. And then we define which device we want to run. We define the loss function optimizer, and then we have the model training loop, right? So it's very standard way of performing any PyTorch training. Now, if I have to do this in a distributed fashion using vanilla PyTorch, I'm just switching it to a train.ddp file, and you will find this file inside this GitHub. You will have two folders, ddp PyTorch only and ddp PyTorch Ray. I am inside the first one, ddp PyTorch only, and you will find this train _ddp.py, right? So this is the file that we have. And this is something that we have seen in the presentation in this case. So let me just pull that. So what we were discussing is this part, right? And then we will move to the Ray part finally. Okay. So let me show you what we need to do when we run it in a distributed fashion. We have to first make that setup, which will have that NECL backend definition, and then we will start the training, and then we have to destroy that setup, whatever setup that we have created. So let's see what is there inside setup. So if you see inside setup, we are doing distributed initial process group initialization with the backend as NECL, and we are defining the local rank. And this is what the torch run will set it up when you execute this code. Okay? So if you have 4 GPUs, everyone will run this code in 4 parallel thread, and everyone will have its own local rank set. Okay? So once this is done, the next thing that we need to do is start the training. Now, if you see the training code, it's exactly same as how you would do in a one GPU setup, but the only difference is now you have to make sure that your data loader is different, because now we have to do the sampling in a different way. And that is what you do here. If you see in this case, we are having the same data set, but now we are using a sampler, which is a distributed sampler, and we are passing the data set there. And so what this actually means is, let's say you have 2 workers and 1,000 samples. What we want when we do a distributed training is the first worker should have 500 samples, and the second worker should have the other 500 samples, right? And who will enable that? Yeah, this is where that distributed sampler comes into picture. If we don't do that, then it would be like same batch of data will go in all the GPUs. And that is not what we want. So this is what this distributed sampler helps us with, right? And how are we going to change this in the code after we loading this data? We just have to come here and make sure that we use sampler.set epoch, so that in every epoch, it performs a sampler in that fashion, right? And we don't send the same data in all the GPUs. And once that is done, we can just save the model checkpoints and call it a day, right? So that is how you will do on a typical PyTorch way. Now, if you now come back and see how we can do this with the Ray Train, it is quite similar, but just a few differences, right? And this is something that will kind of touch base on how this is happening under the hood. Although we have not touched about Ray cluster, but I guess that you will get an intuition of this, right? So, and when you go through the notebook later on, you will understand what is happening. So when we do trainer.fit, this is the architecture of what is happening under the hood. Okay. And we will run trainer.fit in a moment, and you will see that when we run this, under the hood, what the driver will do is it will spin up training workers. So these are like, let's say GPU 0, GPU 1, GPU 2, 3, and so on and so forth. And this train driver will take care of resource management, like which GPU to send, whether to use GPU or not, how to manage the checkpoint and error handling, and so on and so forth. Right? So the key concepts that we learned about in the presentation is whenever we talk about Ray Train, there are two things that is needed. One is your training function, which could be PyTorch, Hugging Face, Lightning, whatever, because the training is still done by the engine that we use under the hood. There is no change that Ray introduces. What Ray does is basically it helps you to scale that into thousands of machines, right, or hundreds of machines or hundreds of GPUs. If you have multiple GPU in one machine, you can very well, live with default PyTorch. But the moment you scale outside that box, then Ray shines. And when you have a Ray train, you need that same code, which you will anyway have. What is extra that is needed here is the scaling configuration. You need to tell Ray that, okay, how many GPUs you want, how many CPUs you want. That information you have to give. And once that is done, it will just, throw that training function across the configuration of your choice. Okay. So now let's see how we can do this. So I'll not go through this, but let me just show you what is happening under the hood. So now we have the data set. Now we will split the data set. We have to shard because we need a different set here, different set here. We will initialize the model, the same model. So we have to make sure that the initialization is synced. We will perform the forward pass. We will perform the backward pass. But before doing the weight update, we have to synchronize. And who will take care of the synchronization? That's the NECL, right? So all reduced primitive will take care of that. And then we will update the model, and we will keep doing this. And at the end, we have to save the model checkpoints. And since this is a distributed training setup and all these GPU have the same model, there is no point of saving the checkpoint in all the GPUs because we are just wasting the resource. So what typically people do is they just save the checkpoint in GPU rank 0 or the first GPU, right? We can always save in all the GPUs, but it's a redundant information. And we will see that in the code, how we make it explicit by an if condition, right? Okay, so let's see how we can do this. So we are importing Ray train and run config, scaling config, and torch trainer, right? These are the torch trainer will glue everything together. And now let's see how that training function would look like, right? So first, we have to get that data loader just like before, but now we have to do that sampling. And that's why we are using Ray Train torch.prepare data loader. So this will take care of sampling and distribution of different batches across multiple GPUs and multiple nodes. Right? So you don't have to worry about how it should distribute your data set. Right? So that's what prepare data loader would take care. Right? And if it sees that you need to run this training in only one GPU, it will not do the sampling, right? So this will take care of all the conditions. And this is the same model that we have, like same vision transformer. But now you have to prepare this model as well. And that is what we are doing here with torch prepare model. And by default, it uses DDP. So remember that I was telling that if you use a different parallel technique, to understand what is happening under the hood, that is not that intuitive. But in terms of implementation, that is very intuitive. Like if you want to use FSDP, you can just say FSDP here. Right? So there is nothing much that you need to do. But to understand FSDP, that might be something we have to spend some time on. But from the implementation standpoint, this is where you will define the parallel strategy. Even if I remove this, it will work because by default, it is DDP. And it will take care of when to move the model to the CPU or the GPU and all of that. You don't have to worry about this. So to summarize, there are two things that we introduced with Ray Train. We prepared that data set with a prepared data loader, and we prepared the model with prepare model API. After that, everything is exactly the same. There is no change in this. In fact, one thing gets eliminated is that you don't have to move your data to GPU. So it will take care by the prepared data and the training function. And the last point is to store the checkpoints, right? So what you would do is you will do torch.save, which will save the model artifacts in all the GPUs. But then if you want to do if you want to save the accuracy loss or things like that after every epoch, you can just do it for the rank 0, and that is what we are doing here. We don't want to throw the same information from all the GPUs because all the GPUs will have the same thing after all reduce, right? So that's why we are just putting it as whenever the rank is 0, because this code will be executed in all the GPUs in all the machines. So we just want to print the loss accuracy only from rank 0 machine, right? So this is what our training function is. Now to start the training, what we have to do is we have to define the scaling configuration. So I'm just wrapping this with another function, but this is not needed. Actually, this function is not at all needed. The reason that I wrote this function like this is because, I can run it through a .py file, not from this notebook. But imagine that this function doesn't exist and you are running it directly, right? So you are defining the training configuration, like how many, what is the learning rate, what is the epoch, what is the batch size per worker. So previously, if you have 100 data points that you are running, or let's say, okay, let me give you like this. Let's say you have 10,000 data points, okay? And you have 4 GPUs. Ideally, what you want 10,000 divided by 4, that is around 2,500, right? So you want every GPU to have 2,500 data points. So this becomes your micro batch size. And this is exactly what we are doing here. We are asking the user to give the global batch size, which in this case is 10,000. And we are finding the batch size per worker by dividing it by the number of workers, right? So these are the training configs, which we will pass. And the run config is, you have to give some metadata about your training run. Things like where it should store the model artifacts or checkpoints. So this is ideally a shared storage. It can be an S3 or a local NFS mount or whatever. But this is where you will define your storage path. This is where you will define what should be the name of that training run, etc., etc. So this is all your configuration. And once this is all done, the training, the scaling config, run config, then you can glue everything together with torch run. So just to emphasize what we are doing, we discussed this part, right? So where you have the training function, then you have scaling config, run config, and all of this, and you are gluing this together with torch trainer, right? And in this torch trainer, you just say which function to run, the training config, scaling config, and run config. And once that is done, you just, when you run trainer.fit, it just distributes the training and perform the training at scale. Okay, so that is what Ray Train is at its core, and how easily you can perform a distributed training at scale. Okay, so now um, since we covered this much, let's see how you can even do better by using Ray data with Ray Train. Right? So as of now, what we did was we used the PyTorch data loader, and then we used Ray, and under the hood, it uses Torch, right? That is what we did. Now, what we are saying is, and this for this we used Ray Train, right? But now what we want is, we want the same thing, but we don't want to use a PyTorch data loader by default. We want to use Ray data to create the dataset or data loader. And then we will use the same Ray dataset in our PyTorch code. And there is a benefit for that. And let me just give you an intuition of that benefit. And then we will see the code, how it is different than what we have been using so far. Right now, we can always live without Ray data. Okay, so let's pause for a second and address this. We can always use Ray Train to perform the training at scale. Now we are kind of optimizing this training, how we can better utilize the memory and make this training even more efficient using Ray Train and Ray data. Okay, so before this, I just missed to summarize. This is the same diagram that we have seen before, but now it has demarcation that which part is taken care by what part of Ray Train. So we are preparing the data set with prepared data loader. So this is the section which shards the data and pass it across multiple GPUs. The prepare model will take care of the model that it is distributed across multiple GPUs and nodes, and the train.report will take care of the checkpointing. Right? It is just a visual way of showing what we have implemented. So the last thing is how we can replace a torch loader with Ray data. Okay, so and then I'll take some questions. Okay, or let me just, I see there is a okay, there is a Q&A. I'm sorry, I did not see that before. Okay, let me come back to this questions. Okay, so let me just before we step to Ray data, let me take these questions. I'll start from the very bottom. Okay, so I just noticed that Q&A here. What happens when you do not wrap the model with prepare model function? So what happens is, if you don't do that, then there is no way that PyTorch would know that this need to be run in multiple GPUs. There should be somebody who should tell that, okay, now take this model and distribute across multiple machines or multiple GPUs. So prepare data would, under the hood, will use distributed training module of PyTorch. So let me just show you this now that you asked. Okay, let me just go here. Okay, so let me just copy this prepare model, and I just, let's see this. Okay, it's a good question. So if you see here, under the hood, it uses, if I just scroll down, under the hood, it uses the PyTorch distributed package, which is the same PyTorch distributed that you would have run if you run it in a vanilla PyTorch, right? So you can either use FSDP or you can use DDP, right? So by default, it is DDP. That is what you are passing. So this will take care of that. You don't have to go to the underlying layer of PyTorch and mention that. So Ray prepared data training model will take care of that. Okay. So let me know if that makes sense. How can we monitor the training metrics? Some kind of log back in ML flow. Yeah. So you can always check the metrics through the API, and also if you come to Ray dashboard, and in fact you can see the cluster status, like if you have multiple GPUs, how that GPU is getting utilized and all that. I have 2 workers, each with 4 GPUs, so you can see that here. But also, if you want to have a workload specific monitoring, you can come to train, you can come to each training run, and you can see all the metrics, how the GPU is performing, how the training workers are scheduled, what is the global rank, local, everything you can see in this dashboard. Okay. Okay, so I think there is one more question, then I will just go back to the Ray data before we close this. So there is a question, when the model is updated through a backward or forward pass and you create a snapshot, you do not need to load the model shard again in the memory, right? Yes, that's correct. So it's not a snapshot, it's actually copying the model. So whenever, I think the question is, when we were discussing about 0, 1, 2, 3 or FSDP, that's correct. If let's say, if consider, let us consider, let me just open this slide so that it's better to visualize. Give me 1 second. Okay, so yeah, so let's say we are here, right? So let's say we are here and we want to perform the backward pass. In this case, we cannot do this because we don't have the optimizer states. We cannot update the model. So in that case, what will happen is you have to communicate, right? And after that communication, we can update the parameters. Once that is done, we will just discard that, right? And this is what we will discuss when we talk about FSDP in details in next webinar. This is just an introduction of how you can get started with distributed training. Okay. All right. So let me just go back and show you quickly about how you can optimize this training even further with Ray data. And this is the last thing that I have for today. So typically, how we are using this training using PyTorch data loader is we load the full data set using PyTorch data loader, and we may perform some pre-processing and then pass it to the training workers. But everything is happening in the GPU, right? So let's say this is GPU 0, this is GPU 1, everything is happening in the same GPU. Now, what happens with Ray data is you can actually do the pre-processing in the CPU and do it in a batch and streamed form. And what the Ray train would do is, after every transformation that Ray data will do, let's say you want to crop the image, do some augmentation, whatever, and that may not need GPU, Ray data will do that in the form of batches. And you can think of batch as a chunk of data. It will do that in the form of batches. After that, it will store it in some memory. So you can think of it as in the RAM. And that memory or that object stored, the GPU node can take from. So the Ray train will read from there and start the training. So there are 2 things happening at parallel. While this training worker is you're processing some batch, at the same time, you are pre-processing using Ray data under the hood, right? So you get a better utilization of the resources, and also it gives you more granular way to manage your entire ML pipeline, right? And it's way more efficient. Now, this is not a deep dive on Ray data, but this is the intuition that you can have in this context. So now when we see the code, the difference in the code is just how you read that data. So now we are creating the data set by reading using Ray dot data read parquet, and we have a lot of different APIs like read parquet, read CSV, so on and so forth. Right? And once we have that, once we created this data set using Ray data, all we have to do is we have to use that in our training. So this is completely separate from your training code now, right? So you have isolated that. For example, this is your, let's say, the transformation that you want to do for every data point. And what you can do is you can just simply say train dataset dot map. So there are two functions that we have, which is predominantly used. One is map, which will do it for each row at a time. Or you can use map batch, which is more preferable, which will take a batch and perform that at the same time. Since this data set is very small, we are using map, but imagine that you have a big data set, so you will typically use map batch. Once you have this, you will use this data set in your training loop, right? So if you see this in the training loop, you are using that. Now, how you are using this, we are using raytrain.get dataset shard. We are calling it train and valid. So that means this information must be given to raytrain somewhere. If I just hide this, and if I just show you the torch train now, you see this, we now passing the data set in a dictionary with train and valid, two different data set. And Ray train will automatically fetch that from the object store. So that is the integration that we have with Ray train and Ray data. Previously, in the previous code, you will see that this line was not there. This line was not there. And in the training function itself, we defined that data loading using torch loader. Right? So that is the only difference. And after that, the training goes, as before. Okay, so that's about how you can utilize Ray train with Ray data. So let me go over some of the questions. How does Ray partition the data between GPUs? Is it a random partitioning? Okay, that's a very good question, Salman. Okay, so that is not, I was expecting this question. So, okay, so let me just show you how we do the data partitioning, okay? Give me 1 second. Okay, so if you see here, okay, so let's say I have this data set. I read this data, and this is not a regular Python list, but it is actually a distributed data set which splits into chunks, right? And but how this happens? So under the hood, you can imagine that if you have this data with multiple columns and multiple rows, what Ray would do, Ray data would do under the hood is it will split into multiple blocks, okay? And there's a block size that we have, 128 MB, but you can imagine that a chunk of rows is one block, and these blocks are basically row tables, right? And that's how it is implemented. And then when you run any processing, it all happens at the same time in multiple CPUs or GPUs, whatever you want, right? And you can perform multiple operation by chaining like this. You read from pandas, you add some column, you do some processing, you do again another processing, and all of this is happening in a batched format. And if you want to get an intuition of this, without Ray data, if you have some data and you want to do some transformation, you will load into the CPU. Once that is done, you will do some transformation. Once the whole transformation is done, you will do the next transformation. And after that, you will send it for training or inference or whatever. But while this happens, the GPU does nothing. But what happens with Ray data is, since it is doing it in blocks, and block is the smallest unit of smallest unit on which Ray operates. You cannot chunk between the block. And what this enables you to do is, while you are processing the first block, once that is done, you send it to the next transformation while doing the next block processing, right? So that's how you make your resource utilization better. And with the context of our webinar today, if you look at this bottom section, what is happening is, after using Ray data with Ray Train, after this part, right, this is being read by a Ray Train, right? And Ray Train will take this and start the training, while Ray data is doing the next data loading. So I'm assuming that there is no transformation. If that is the case, if that is the case, in that case, let's say after this, this is not for inference, this is for training, right? So the training will start here itself after this transformation. And while the training is doing on this block of data, the Ray data is already working on different blocks. So that way, you are utilizing your resource in a much better way. Does that make sense, Salman? Yeah. Okay, so if you want, I can share this deck as well. Yeah. Okay, so I just want to let you know that Ray is amazing. How we had hard time to scaling Django with Ray. Okay, that's good to know. Thanks. Yeah. Thanks, Adarsh. Does Ray Train ensures 100% GPU utilization? No, so I think it's a very subjective thing. You can always check the resource utilization, but you need to do that. From the resource utilization standpoint, you need to know how much data you are pushing and how big your model is, and then you can see. I would always recommend to start with a smaller batch of data and see that how utilization is happening. And in fact, if you want to know, how you can do all those calculations, you need to know a little bit about the math behind it, like what exactly we are throwing before we get and one of the resource that I have, okay, I guess I have not shared that. So let me share this first. There is a blog that I wrote. So this a very detailed, like it might take some time to go through this, but this has all the details in a more mathematical way, like what is happening under the hood. And later on, whatever we have covered, it is mentioned here. But just to your point, you can pick the model, do some calculation and see that, okay, this is what I'm heading towards. I expect this to saturate 80% of the GPU. So let's start with this, right? And because there is always some overhead for communication and all this, right? But Ray will make sure that your resources are effectively utilized. Now, how you would know? For that, you have to do some homework before you start anything, right? But I will recommend to start small and see from there. So this is the GitHub repo for this. This is the blog that I just shared. Right? You may like to go through this. And again, I will share this deck. You might get an email by today, tomorrow. And then this is the session that we have on FSDP next month. So we will go little deep on the FSDP side. We will not cover this basics, but yeah, if you're interested, you may like to join. And if you have any questions or queries, feel free to ping me on LinkedIn. I'll be more than happy to answer. Okay, so I'll just I think we are almost 10 minutes ahead. I mean, not ahead, 10 minutes past, but we can have 5 more minutes so that we can go through a few of the other questions. So let me see if you have some other questions which I have not covered. There is a question. Ray automatically take care of interdependent tasks. Yes, so Ray will take care of the scheduling of the task. So Ray, when you perform any task or when you do anything with Ray, Ray has a head node, and it takes. And this is the node from where we are running this notebook and all. So every worker node is responsible to share what is happening in those nodes, how many CPUs, GPUs, and tasks are running, and which are free or not free. So every 100 millisecond, it just sends broadcast its resource utilization, and the global control service within the array head node, it will take care that everything is happening under the threshold, right? So that resource scheduling, resource handling is array's task. Okay. Okay, I think this is a question which was asked, like, what is GDP? I think you got the answer. It's distributed data parallel. Free credit is good enough for this notebook? Yeah, absolutely, yes. So it's like you can very well do this within your free credits. I don't think it will cost you more than $1 or so, right? Or a few cents, actually. No, not dollar, a few cents. Okay, so I guess we are good. So in case you have any further questions, again, feel free to share, and I'll be more than happy to answer on LinkedIn. And if you have any specific questions, you can also send me an email at suman.@anyscale. Okay, so once again, thank you so much for your time. I hope that you learned something new, and I'll look forward to meet you in a couple of weeks when we discuss about FSDP. Thank you so much.